morning or good afternoon. My name is Jacqueline Rodriguez.
My name is Deepthi Sarnpuri.
And my name is Sarah Thompson.
And we will be presenting on X-rays. A brief overview of what we're going to be discussing today. We will be talking about what are X-rays, the definition of X-rays, the characteristics in the EM spectrum, the history of X-rays, how X-rays work, the physics behind X-rays, medical applications of X-rays, and the dangers of X-rays.
What are X-rays? X-rays are a form of ionizing electromagnetic radiation. They have a very high frequency and a short wavelength. They have an inverse relationship between the wavelength and frequency because the speed of light is a constant. It's able to pass through many materials opaque to light, and wavelength ranges from about 0.01 to 10 nanometers. And it's energetic enough to pass through the human body. Here we can see the equation for the relationship between frequency and wavelength. Frequency is equal to the speed of light over wavelength, which is represented by lambda. So this equation is also rearranged down here where lambda, or wavelength, is equal to the speed of light, which is equal to 3 times 10 to the 8 over the frequency.
Now we're going to do a practice problem. So the problem says that a dental hygienist uses X-rays of a wavelength of 1 angstrom to take a series of dental radiographs while the patient listens to a radio station that is at a wavelength of 325 centimeters. And they look out a window with blue light, or at the blue sky, which is at a wavelength of 473 nanometers. What is the frequency of the electromagnetic radiation from each source? So what we're going to do is we're going to do each question, or each part of the question. And since we know this equation, as Deepthi mentioned earlier, where frequency is equal to the speed of light over the wavelength, and we know the speed of light, since we're given each wavelength, we can find out the frequency at each wavelength. So in the first equation, in the first problem, we're given that the wavelength is 1 angstrom, but we need to convert that to meters. So what we do is we have the 1 angstrom times 1 times 10 to the negative 10 meters over 1 angstrom. So that way we can get 1 times 10 to the negative 10 meters for the wavelength of X-rays. Since we have our wavelength, we can now plug it into the equation, and we find that frequency is equal to the speed of light, which is 3 times 10 to the 8 meters per second, over 1 times 10 to the negative 10 meters. And that gives us a frequency of 3 times 10 to the 18 hertz. In the next problem, or question, we are given that the wavelength is now at the radio wavelength. So we're given that it's 325 times 10 to the negative 2 meters. So we plug that into the equation. So we have the speed of light over the wavelength of 325 times 10 to the negative 2 meters. And that gives us 9.2 times 10 to the 7 hertz as our frequency for the radio wave. And now for the third problem, we're given visible light, which is measured at 473 times 10 to the negative 9 meters. So we plug that into our equation. So we have the speed of light over 473 times 10 to the negative 9 meters. And that gives us a frequency of 6.342 times 10 to the 14 hertz.
So an important physics concept that applies to X-rays is the electromagnetic spectrum. X-rays are formed by ionizing electromagnetic radiation. So if you look at this image, we see that it starts with gamma rays and it moves to radio waves. So as we move to the right, the wavelength increases as the frequency decreases because wavelength and frequency are inversely proportional to one another. At the same time, as the frequency increases, approaching gamma rays, the energy also increases. So X-rays lie right here on the electromagnetic spectrum, which means that it has a relatively small wavelength and a relatively large frequency. meaning that they contain a lot of energy, which is why it is typically dangerous for humans to be exposed to X-ray radiation for an extended period of time. So in general, X-ray wavelengths fall between 0.01 to 10 nanometers, and the frequencies range from 3 times 10 to the 16th to 3 times 10 to the 19th hertz.
So X-rays were discovered on accident by Wilhelm Röntgen on November 8, 1895. He was working with cathode radiation to find out if other rays would radiate from it. In order to do this, he evacuated all the air from a tube and then filled it with a special gas. The tube would then produce a fluorescent light when a high electric volt was passed through it. So Röntgen found that X-rays could pass through the tissue of humans, leaving bones and metal visible. One of his first experiments was on his wife's hand. As you can see here, you can see her wedding ring and her bones, because both of them have dense enough material that the X-rays cast a shadow.
A continuation of some history of this, when the news of his discovery spread quickly throughout the world. Cathode tubes were very well known during this time period. Other scientists were able to duplicate his experiment, which only further validated it. X-rays were being utilized in clinical settings in the United States in as early as 1896. They were used for bone fractures and gunshot wounds.
Light is a form of electromagnetic radiation. At some wavelengths, it appears as visible light. At others, it takes the form of radiation we cannot see, such as ultraviolet, infrared, and X-rays. X-rays have very short wavelengths that, unlike visible light, are able to pass right through most tissues in the human body. Since bones contain calcium, a denser material than most other tissues, they are able to stop some of the X-rays and can thus form a shadow. If you place your hand in front of a flashlight, it will cast a shadow on the wall behind it. In a similar manner, X-rays directed at the body produce shadows on the opposite side that can be registered on film or on a digital sensor, so that bones are clearly visible while soft tissues, such as muscle, are shadowy. As a result, the two-dimensional images formed by the X-rays are quite useful in revealing structures within the body and can easily display fractures in bones.
So how exactly do X-rays work? If you look at this image over here, it illustrates an X-ray tube. And X-ray tubes are powered by a circuit, as you can see here, and the circuit typically has a voltage ranging from 20 to 100 kilovolts. So what happens is that an energetic beam of electrons is generated and directed at the metal target, which in this case is tungsten. And when the electrons collide with the target, X-rays are emitted. So the cathode is the negatively charged side, while the anode is the positively charged side. So when the electrons move toward the positive side, they decelerate, which is what causes radiation in the form of X-rays. Only about 1% of the electrons that pass through the X-ray tube produce X-rays, while the other 99% is lost in the heating up of the target metal. Typically, there are two different types of X-rays. First one is soft X-rays, and the second one is hard X-rays. Soft X-rays are what we typically use in the medical field, and they have low energy photons, while hard X-rays have high energy photons.
This is practice problem number 2. An X-ray tube is operated at a peak voltage of 100 kilovolts, and the beam current is 40 milliamps. So what we will first find is the power of the machine. The equation for power is P equals VI, volts times current. So the volts in this problem are 100,000 volts, which is equal to 100 kilovolts, which is given in the problem. and the current is 0.04 amps. So in order to find power, we multiply the volts times amps, which gives us 4,000 watts.
Next, the question is asking us to solve for how many electrons reach the machine every second. So the equation that we're going to use for this problem is the number of electrons per second is equal to the total charge divided by the individual charge of each electron. So from the problem, we know that the total charge of the X-ray tube is 40 milliamps, which translates to 0.04 amps. And you divide that by the individual charge of an electron, which is 1.6 times 10 to the negative 19. So when you compute this, you get the answer of 2.5 times 10 to the 17 electrons per second.
Now we're going to find how many photons are released every second. So as we mentioned earlier, only 1% of the electrons actually emit X-ray beams. So this is the number of electrons per second that we found earlier. And by multiplying this, we end up getting the answer of 2.5 times 10 to the 15th per second. So that's how many photons per second we end up with.
So what we will find next is the maximum energy of each photon and its wavelength. In order to find photon energy, we use the equation volts times charge. The volt in this problem is given to be 100,000 volts, seen with kilovolts, 100 kilovolts, and the charge of an electron is 1.6 times 10 to the negative 19. So when we multiply the volts times the charge of an electron, we get 1.6 times 10 to the negative 14 joules as our photon energy. In order to find our wavelength, we use the equation Planck's constant times the speed of light over energy. We just found energy, so we put this into our denominator, and in our numerator we put Planck's constant, which is 6.63 times 10 to the negative 34. And our speed of light is 3 times 10 to the 8th. After solving this equation, we get 1.24 times 10 to the negative 11 meters, or 0.0124 nanometers, as our wavelength.
Now we will look at a quick demonstration of how X-rays work. So just like visible light casts a shadow on opaque objects, when X-rays go through our body, it casts a shadow of our bones onto the plate for viewing. So in this situation, we have a flashlight as our visible light, and we are using my hand as the object. So when you flash the light onto my hand, you can clearly see that in the back, it casts a shadow. So just like this concept, when an X-ray goes through our body, we can see the shadows of the bones on the plate.
Medical applications of X-rays. X-rays are used for medical diagnostic procedures and for research purposes. They are best suited for image of bones. Soft X-rays are used because they cannot penetrate through the patient's body, and they do not add unnecessary risk of radiation damage. Patients are scanned with an X-ray frequency of about 7 times 10 to the 8 hertz, because the human body tissue absorbs this frequency the best. CAT scans use a series of X-rays taken at several angles and are interpreted by the computer to better image the soft tissue.
These are some modern-day X-ray machines. This is a stationary one, while this is a portable one.
X-rays in action. X-rays help doctors see broken bones. For example, in this picture, we can see that the leg is fractured and split in two. And the X-rays can also be used to help detect damage in the lungs caused by tuberculosis in this example. Computers can now make X-rays in color, which is why we can see the damage here is in red, versus in this picture where it's simply black and white.
Hi, I'm Dr. Kate. You might be nervous when you hear you need to have an X-ray, but X-rays don't hurt. They're an easy way to give doctors an inside picture of your bones and organs. Here's what happens. Depending on what part of your body needs to be X-rayed, you might have to put on a hospital gown. You'll also need to take off all jewelry, watches, and glasses. Metal gets in the way of taking a clear picture. The X-ray technician, tech for short, takes you to the room with the X-ray machine and a table to sit on, lie on, or stand beside. Think of the X-ray machine as a giant camera. The tech will help you get into the best position for the X-ray. You can help by trying to hold very still. Then the tech will move to a little room nearby where she'll press the button to take the X-ray.
Here we go. Stay still.
This usually is very quick. You'll probably hear a clicking or buzzing sound as the picture is being snapped. The tech will tell you when it's okay to move.
Okay, picture's done.
Next, the tech might come in and help you change positions to get a different view. When it's all done, you can get dressed. That's it. Your doctor will soon get the X-rays. If you want, ask if you can see them.
So as we mentioned before, because X-rays contain such a high amount of energy, there are many risks that come with having X-rays done. So at the molecular level, RNA and DNA can be damaged and the metabolic pathways are interfered with. And as a result, our genes can get mutated. On the cellular level, X-rays can damage cell division and it can cause our cell to die or be transformed to malignant growth, which translates into cancer. On the subcellular level, cell membranes, nucleus, chromosomes, and mitochondria can be damaged. And lastly, on the tissue and organ level, it can disrupt the central nervous system, cause death of bone marrow, disrupt the lining of the gastrointestinal system, leading to sickness and death, and it can also cause cancer.
Hi, I'm Ray with Gateway Radiology in Pinellas Park, Florida. The question is, what are the risks of X-rays? The risks of having an X-ray done, diagnostic X-ray, are minimal at most. They range anywhere. It begins really at the cellular level, so there is damage done at the cellular level that tends to accumulate over time. It doesn't go away, so the risk becomes when you are exposed to series after series after series of X-rays over years. Most patients that have routine diagnostic procedures or X-rays done, the risk is minimal at most. Patients that do have prolonged procedures, repetitive procedures over years can start to see side effects of it, but generally in the diagnostic level of X-ray that doesn't happen. Some of the risks can be cataracts. That is a big risk. That's why many of the technologists that work in the field do wear the lead because they are exposed every day to this radiation. So they wear lead aprons and they wear lead glasses or goggles to protect their eyes and the rest of their body from the radiation. Then the rest of the effects go into the blood-producing bones. We protect those. That's why we will have lead aprons placed on patients when you go in for dental X-rays or routine X-rays. We protect every area, or try to protect as much of the area as we can from the radiation, so that there are no real risks or effects of the radiation. Again, the risks are very minimal in diagnostic. Usually the benefits of having an X-ray far outweigh any type of risk that you would have from the radiation. And in the hands of the trained technologist who's been schooled, we keep the dosing of the radiation at a minimum to reduce those risks. Again, I am Ray with Gateway Radiology in Pinellas Park, Florida, and those are the risks of X-rays.
Some preventative measures taken to avoid electromagnetic radiation and its harmful effects are lead vests. So you'll see in your doctor's office or in your dentist's office lead vests hanging, and whenever you get an X-ray, they'll make sure that they cover you as much as they can with it. This is because lead vests are made out of a more dense material which blocks its radiation from getting to your body. In everyone in general, it is very important to protect both the sex organs and the thyroid, since they have the highest sensitivity to radiation and are the more susceptible to mutations. Thank you so much for watching, and I hope you enjoyed our presentation. Thank you.
Thank you. And these are our credits.